Okay. Let's get started. So, I have this definition written up here. Give me a sec, I'll come to that. For now, I just need to kind of introduce what a series is in general. Okay, so last time we talked about sequences, okay, and generally in a sequence, right? What's going to happen is I just list A1, A2, no, A3. I just have a bunch of numbers kind of listed together, okay, and that's going to be my general idea of the sequence. I'm not doing anything with them together. They just, each one kind of exists independently, okay? But what if I decided to take all the numbers in that sequence and I wanted to add them together? Okay? If I did that, okay, then we're not just dealing with a sequence anymore. We're dealing with what's called a series. Okay? We write it generally as the sum from n equals, in this case, it'd be 1 infinity, sometimes we'll see 0 down there, of an equals a1 plus a2 plus a3 plus da, 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 okay? So essentially, in a series, we always go from some number to infinity. And what's going to happen is I'm going to take every number, you know, every possible output of this sort of sequence, and I'm going to put them all together. So I'm going to add every single term together, right? So we had, you know, we did 1, 2, 3, 4, 5, 6, 7 as an example yesterday, right? And so my series would just be, I would write it like this first, and then we would 1 plus 2 plus 3 plus 4 plus 5 plus 6, right? Now, that's a nonsensical series. That's like it's kind of weird to look at, right? Because those numbers are only going to keep getting bigger, right? So if I take 1 plus 2 plus 3 plus 4 plus 5, that's only going to keep getting bigger, right? That's just the numbers keep getting bigger, right? Now, some of you, you know, if you are spending time looking at math outside of taking classes, you might have seen somewhere of a download group where you see this negative 112. That's not an actual reality. But so this one's a little weird to study. However, there are some series that we can actually get something out of, right? And so to give one, for example, let's kind of look at the sequence. And so I'll write the general A in term for now. 1 over 2 to the nth power. Okay. If I take all these terms and add together, right? Let's so we're going to take the sum as n equals 1 to infinity of an. This is going to be a1 plus a2 plus a3 plus dot 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 dot. This is the same thing as 1 over 2, right? Because that's 2 to the first power. Plus 1 over 4, right? Plus 1 over 8, because we do a 3, plus and then be 1 over 16, dot dot dot. Okay. Now, in this case, right, the numbers keep getting smaller, so there's a potential there's actually like something interesting about this. There's something that comes out of it. Okay. The way we're going to kind of determine if there is something that pops out is let's not take the whole sum at once. Let's just take little pieces of it, right? So what I mean by that is I'm going to do what's called its partial sum. Okay. So again, we're given this series, we're going to let Sn denote it's the nth partial sum. So that means that instead of adding all infinity terms, I only go up to some nth term. Okay. So let's find S1, for example. Okay, so S1 in this case, I'm just going to take the sum from I equals 1 to 1 of AI. Okay, so how many terms am I going to be adding here? Just one single term, right? Because I go from 1 to 1. There's only one value, right? So it's just A1, just in our case, is 1/2. Okay, now let's look at S2. Okay, S2 is going to be the sum from I equals 1 to 2 of AI, right? So I'm not just adding A1 now, I'm doing A1 and A2, okay? Which A1, again, is 1/2 in this case, and A2 is 1/4. So what is, can we do 1/2 plus 1/4? What is it? 3/4. We get 3/4, right? Good. Now, if I were to do the next one, I would do the same thing, the sum from I equals 1 to 3 now of AI. And so I do 1/2 plus 1/4 plus 1/8, which is going to be end up being 7/8 in that case. Essentially, I just add 1/8 to this, or you can just do it each point, right? Now we're going to start seeing a pattern here, right? Because the next one would be S4 would be 15/16, and S5 would be 31/32 if we added them. So what's happening, right? On the bottom of each of these little partial sums here, I have basically kind of what the 2 to the power at that time, right? So in this case, I have 2, 4, 8, 16, 32. What's happening to the number on top? Like how, so again, we have 1/2, 3/4, 7/8, 15, 16, 31, 32. How is that top number related to the bottom number? So bottom minus 1, right? So what we're seeing here, right, if you want to get a general formula for it, right? So you can kind of take this as a sequence, right, where I have, so Sn. So we'll think about it as a sequence, right? The sequence of these little partial sums. So we see we get 1/2, then 3/4, and 7/8, and 15/16, 31/32, etc. Right? Now we can get a general formula for this, right? Because this should be S1, S2, S3, S4, S5. Right? What we're seeing is for Sn, the general term is I get 2 to the n on the bottom, right? Just 2 to the whatever the number is, right? And then on the top, we're going to get 2 to the n power minus 1. I just take the number that's on the bottom, I subtract 1 from it. Okay? But another way I can write this is going to be 1 minus 1/2 to the n, right? I just divide the 2 to the n from both terms. Okay, now let's think about this, right? If I take n and I keep making it bigger, right? What's going to happen to this fraction? It's going to keep getting smaller, right? So yeah, each time we get 1/2, 1/4, 1/8, 1/16. It's just going to keep getting smaller, right? So what we're going to imagine happens is as I take this all the way to the end, is that this should just be 1, right? Because it's going to be so small that I'm not subtracting anything. And indeed, that's the case, right? We talked about doing sequences last time. If I want to see what those sequences converge to, I just take the limit as n approaches infinity of the Sn term, and this little partial sum, which is going to be the limit as n approaches infinity of 1 minus 1/2 to the n. But this is going to end up going to be 1/infinity, which is 0. So we're just left with 1. Now, what that means is that our sum here, this 1/2 plus 1/4 plus 1/8 plus 1/16, this is actually equal to the number 1, right? Because this Sn was each partial sum, right? Was each like, as I add the next term, what's going to happen? As I add the next term, what's going to happen? As I add the next term, what's going to happen? So since that partial sum ends up slowing down to 1 at one point, it kind of stops adding, right? We can conclude that this whole sum, when you put everything together, ends up being the number 1. Okay? And so that kind of comes, so we have our definition here. So Sn denotes the nth partial sum. Sn is going to be the sum from I equals 1 to n of AI. Now I'm gonna give you a way to kind of digest this a little easier than what's here, but we need to introduce the concept, which is having them like know where we're coming from. If the sequence converges, which it did in this case, converges to 1, and its limits exist as a real, like it's just some real number, it's non-infinity, then the sum is called convergent. Okay, so in this case, since we found a number out of this, we got the number 1, right? This is a convergent series. Okay, so if a sum, right, this is kind of the, if you can find the sum, this is how you determine if it's convergent or divergent, right? So if the sum exists, it's a real number, right? It comes to it, then it's converted, okay? And then we can say that this kind of the limit of the sequence, that sequence of partial sums is going to be that, what that series is going to be. Okay, so again, in general, right, we may take some sequence and it's not really going to go anywhere. It's not going to end up looking like something we want, right? 1 + 2 + 3 + 4 would be infinity, right? But there are some that are going to, the terms get small enough to where after you add bar enough, it's going to be, you end up getting a number out of it and squeezing something out. And so that's what we're going to look for when we talk about series. Okay, any questions for me on this at all? Nope. Okay, good. So let's take this, and maybe I'll do, let's see, there's still examples here. I might do number 18. Okay, so let me talk about this example here in the book real fast, which says, kind of breaks down this idea, and it says calculate the first, or sorry, it says calculate the sum of series whose partial sums are given, right? So we're given, we have some series, which is n = 1 to infinity of n. And then we're given its partial sum is n squared minus 1 over 4n squared plus 1, right? And so we want to find what the sum of this thing is by knowing kind of how each of the partial sums come together, right? So all I need to do for this question, right? We said, right, we had a sequence of partial sums, right? And we took the limit of all of those little pieces, the little partial sums, and put it together. That would be the sum of my series, right? So what do I need to do to this to find the sum? Take the limit. Anybody want to tell me what the limit of that thing is? It's 1/4. Yep. Because we have n squared and n squared, just take the coefficient. So the sum of the series, if this is in partial sums, it's just 1/4. Take a limit of it. Okay. So we kind of used this idea of a sequence. We took the series, kind of broke it down to a sequence, and that sequence helped us to get out the sum in general. Questions for me on that at all? If it spits out a value that's not infinity, it's conversion. So yes. Okay. Now we're going to not want to have to do these types of problems always like this. So it's useful to know, obviously, how to get there. But we want to find an easier way to work with these. Okay, so to start with, we're going to take kind of an easy example of a sum. Okay, which this actually falls into that category. But we're going to make it more general. Okay, and what we're going to do is we're going to look at something called a geometric series. Okay, so again, we knew the partial sums of the last ones, we took the limit and that's it, okay? But I don't want to do that every time. I want to be able to be given a series and be able to just tell directly what's going to happen, or be able to set it up in some way to cancel out rather than me having to do all the hard work of going through making the sequence sort of thing. Okay, so we're going to look at the geometric series. Okay, so when I talk about geometric series, okay, the term, and I'll call it Vn for now. Kind of that the term that's going to be in each piece is going to look like some number a times r to the n power. Okay, so this is our general format. We have some r number raised to an n power, and then multiplied by some a on the outside. Okay, now to. Okay, so in this case, I started at 1 there. We'll start at n equals 0 here because that's perfectly allowed. We'll just add an extra term. But so what's going to happen again, kind of fitting into this mold? I want to add each of these terms together, right? So another way to see this is I'm thinking there infinity and AR again and add together. So in each case, like let's kind of see what each of these pieces look like. Okay, so if I put 0 in for n, what is that term going to look like? So we get 1 and then times a, right? So we get a plus. Okay. Now, what happens when I put 1 in there? AR. Okay. Then we're going to get AR squared plus AR cubed. Okay. So that is what our series looks like. I'm taking a, and then a times r, then a times r squared, then a times r cubed, then a times r to the 4th, then a times r to the 5th. Yes. Where's the n supposed to be? That's just I was trying to, kind of fit it with what we're doing here. That's kind of like the defining term of the sequence, essentially, for that, but we're adding all these together. So just to kind of connect it, you don't necessarily need to have it there, but just help a little bit. So Bn is AR to the n. Okay. So we want to find the sum of this series in general. And if we do, that'd be nice because we have a lot of series. So we're gonna be a little tricky on this though, so we can get the sum. Okay. Because again, the only way we know how to get sums at this moment is by looking at this sort of partial sum. Okay. So let's take the partial sum of this guy, just the S there. Okay, so, oh wait. Oh, my bad. Give me 1 second. This is supposed to be AR to the n minus 1 in this case. Not just AR to the n. It depends on if you use 1 or 0, how it all functions. Well, it'd be n minus 1 if we wanted n to be 1 down here. But if it's n is 0, I'll go to the book right now, just for the moment. I might be able to fix it from that point and kind of adjust it. But let's assume we have n equals 1 and we have AR to the n minus 1. Still the same thing, right? Because I have a 1 in there, I get 1 minus 1, which is r to the 0, r to the 1st, r to the 2nd, etc. Okay, so it's still the same sum. Okay, now here's what I'm going to do. Let's look at the partial sum of this thing, right? So if I just go to the nth term, okay, I'm going to have a plus AR plus AR squared plus AR cubed plus dot 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 plus, and we're going to start at a times r to what power? Or we're just going to the n. Yeah, semi. Good. So that is what our partial sum looks like. Okay. Now, let's think about what's going to happen if I take. So again, we're going to be a little tricky here to make this. What if I take this thing and I multiply both sides by r? Okay, so I have r times that partial sum. Now, when I take r multiplied by this left side, what do I have to do to the right side? Yeah, I'll multiply r by every single term. So I'm going to get a times r. I'm going to get r times AR squared, r times AR squared. Okay, all the terms again, right? Yeah, I get AR to the n minus 1, right? The one before it, and then I multiply this one by r until I get AR. Yeah, so yeah, essentially just it kind of adds an r to each term and shifts over, right? And I shifted it over so we can see this. Okay, now what's going to happen if I take these two things and I subtract them? On the left side, I'm going to get, and I'll write it as 1 minus r times s, right? Because Sn is in both of them, so I can just pull out the Sn there, okay? So I get 1 minus r. On the right side, we have A, of course. What's gonna happen to all the terms here in the middle? Right, so I have AR minus AR squared minus AR squared, AR cubed minus AR cubed. But yeah, so everything in the middle here, and this block is gonna cancel out. So the only term I'm gonna be left with here is this AR to the end, and since there was a minus, it's gonna be minus A, and maybe I'll go back to that out. So I get this. Okay. Can I solve for Sn? Absolutely. So I get Sn equal to A times 1 minus r to the n over 1 minus r. So instead of having all this dot 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 stuff here, we don't need it. We can just write it like this instead. Now there's a little bit of a note. This depends on if the converges or not, but we'll assume it converges, right? Because if it doesn't converge, then our answer would be nonsense. Okay. So if I want to find the whole sum of that series, right, and this is the partial sum, what do I need to do? Take the limit of it. Okay. So we're going to take the limit as n approaches infinity of A times 1 minus r to the n power over 1 minus r. Okay, now this depends very much on what r is, right? Because we talked about this yesterday. If r is a big number, right? If r is like, 2, 3, 4, it's something bigger than 1, it's just going to explode, right? Because then I'm going to take r to this n power, right? So in that case, not really going to be very sensible, okay? What we're going to do instead to do this is I'm going to assume -1 is if r is in between -1 and 1. Okay. Again, we talked about this yesterday. In order for that sequence to converge, we needed r to be like that r value to be. So it would get smaller. Otherwise, it would just keep getting bigger, or it would oscillate so much. Okay. Now, if r is in between -1 and 1, what is the limit of that term? So what is r to the n? What's the limit of that going to be? It's 0. I have something smaller than 1. If I have something smaller than 1, I take a power of it. The number just keeps getting smaller. Smaller and smaller and smaller and smaller. Right? Until it just becomes 0. So the limit of this thing, that r to the n is going to become 0. And I'm going to be left with A over 1 minus r. Okay, it's going to be very useful to remember. So let me go ahead and write out that general formula for us. So in the end here, if I have the sum from n equals 1 to infinity of AR to the n minus 1, then this series is equivalent to A over 1 minus r. But this is only true when r is in between -1 and 1. Okay? Again, let me reiterate. If r is bigger than 1 or smaller than -1, this thing explodes. Okay? It explodes a couple of different ways, depending on which direction you go, but it still explodes. Okay? And it's something we don't want. But if it's in this nice range of numbers, then it's going to be equal to A over 1 minus r. So here's something we can take away from this. Okay? If -1 is less than r is less than 1 in the geometric series, then the series converges. 2. If r is less than or equal to -1, or r is greater than or equal to 1, the series diverges. Okay. And if it converges, then we know it's sum, and sum is a over 1 minus 1. And if it diverges, then we don't need to worry about the sum because it doesn't mean anything. Just like that negative 1 12 really. It sure get it somehow, but it doesn't mean it means anything. Okay. Questions for me? Yes.
This is the only solution that could be found.
This is the only
Solution that could be found for this series,
for a geometric series.
where R is between negative one.
Yes, it is only if R is going to be negative 1.
You're gonna have one. Three.
No.
Or something.
No, I mean, I'm sure you could if you made it like, yeah, so you could if instead of R, you had R over 3 in here. Yeah, but we don't want to keep making cases like that. We'll just make a general like this. And then you look on the inside and you're gonna say, okay, well, in order for that to be in between negative 1 and 1, then I need that to be. We will get into that more later on. Actually, we'll probably do this. Okay. Good. Okay. Let me actually let's go do a couple examples of this. Okay. So we are to determine, we're gonna have a couple examples here, and the examples are gonna be to determine whether the sum converges or diverges. And then from there, if it's convergent, we're gonna find its sum. Okay, so the first one I have is gonna be number 18. 18, we're gonna have the sum, which is gonna be 4 plus 3 plus 9 over 4 plus 27 over 16. Okay, so to be able to determine anything, I need to see if I can get into that one. Okay, because obviously if it's it calls it a geometric series, so we know it's a geometric series. We just have to figure out what its general term is. Okay, so let's kind of figure it out. Right, let's treat this as if we were doing the sequence. Right, let's just look at each term and try to figure out what's going on. Okay. Let's start with, I don't know, what's going on in the numerator, maybe. Do you see any patterns in the numerator?
There.
3. Right, they're powers of 3, right? We have 3 to the first power, 3 to the second power, 3 to the third power, here at least. Okay. Yeah, and so ideally we want 3 to the 0 power. Okay. What about the bottom, the denominator?
4 to 4.
We have powers of 4, so we have 4 to the first power here, 4 to the second power here. We would want this to be 4 to the 0, is that true? Good. And we want this to be 4 to the negative 1. That makes sense. So that's good. Okay. So let's write the general term for this. So an we want n to be 1. So if we want n to be 1, what is this gonna look like? Right, so we need, so whenever n is 1, we need a 0 here, and we need a negative 1 down here. So again, we have 3 to a power, and we have 4 to a power. So what's the power on 3 need to be? And then 4, n minus 2. Okay, again, let's trace it. If it's 1 here, we're gonna get 3 to the 0, good, and we're gonna get 4 to the minus 1. Next one, if it's 2, we're gonna get 3 to the 1 and 4 to the 0. It works, right? Good, so that is our term. So now I want to take it and I want to put it in my sum. We're going to go from n equals 1 to infinity, and then we're going to just take this thing, 3n minus 1 over 4n minus 2. Now we have a bit of an issue, right? Because it's still not exactly what I want, right? I want to have n minus 1, but right now I have n minus 1 and n minus 2. So, is there any way I can fix that? What do we think? I want to turn this from n minus 2 to n minus 1. we could, well, maybe not just a 4, right? Because we just factor out a 4, you take out 4 to the first, so it actually make it n-3. So what's gonna happen, right, is I wanna make that n-1. So I need to multiply that. I would wanna multiply it by 4 to the first power. Right? Because 1 plus n-2 gives me n-1. Okay, but I can't just multiply 4 on the bottom, I also have to multiply in the top. So I get this, okay? Now this 4, it doesn't matter where I multiply it again, multiplication is commutative, so I can just kind of bring it out in front. So this is the same thing as the sum from n equals 1 to infinity of 4, this 4, times 3 to the n-1 over 4 to the n-1. So we're gonna get 4, and then these have the same power, so what can I do? What is it? You can make it 3 4. So we're gonna have 3 over 4. Yeah, if they have the same power, I can just kind of bring it out and then write this fraction. So this is what I get here. Okay. Now, does this look like this guy? Absolutely, it does. Okay. What's my R in this case? 3/4. Is that in between -1 and 1? Yes, it is. So this is true. So what does that tell me about my series? It converges. Good. Okay. If it converges, we can find the sum. So how do I find the sum? We actually don't need to take the limit in this case, right? We already did that hard part. We can just use our formula. Yeah. We're gonna do n equals 1 to infinity of 4 3/4 to the n-1, which is gonna be, so I want to plug this in. So where does this 4 go? It goes for A. And we're gonna have 1 minus. Okay, everybody see that? Just take the numbers and just plug it into the formula. Okay, so what is 1 minus 3/4? 1/4. So we're gonna get 4 over 1/4. Okay, what can I do with that 1/4? We get 16. That's the final answer. Okay, so that series right there is 16. Okay, so it actually does. Questions? Okay, let's do another quick one. Just get the point across. We'll do let's do I'll do number next one. Yeah, absolutely.
That, A0 is, the square root of 16.
Huh?
A0 is 4 and the square root of 16 is
I think that's just how they set up the problem. There's not really a, like, you can't, if you know this is 4 here, you can't say, oh, I just square that number. It just appears. Like if this was a 1/2 here instead, like it would be different. Okay. Let's talk about it real fast. I want to make sure we have. Well, I'll just do one more real fast. So if I have. Well, if I have this, I want to see if this converges or diverges. Okay, what should I do? So I'm gonna take this 5, right? So this 5 doesn't have a power to it, right? So I'll just kind of set it off to the side of there. Okay. Okay, now I have pi to the n, 1 over pi to the n. Let's ask the question again. We saw it yesterday. If I take 1 and I raise it to any power, what is it? If I take 1 and raise it to any power, it's just 1. Okay. So is it still correct if I call this 1 to the n? Absolutely. So this is the same thing as n equals 0 to infinity of 5 times 1 over pi to the n. Good. What do we think? Is it converge or diverge? Why? Yeah, it's positive, it's less than one, so. Good, right? Pi is about 3.14, so that's definitely bigger than one, so it converges. And we can find its sum, right? Which is sum in this case. Now we started at 0, which is gonna be a little interesting, right? So let's think about that. So notice we're starting at 0 and we have n now instead, right? Now is this and this the same thing? Why or why not? What do you think? So if I take 0 and put it in, I get 0. If I take 1 and put it in here, I get 1 minus 1, which is still 0. Right? So these are exactly the same thing. Okay? So that 1 n minus 1 thing is the same thing as 0, 0 and n. Right? All that changed is that I just made n start at 1, but to count for that, I just made this n. Okay? So it converges, right? And to find the sum, right? So again, maybe I'll write it in general. This is the same thing if I can equal 0 to infinity, just a times r to the n power. But this is going to be a over 1. Okay, so it converges, so we just do a over 1 minus 1, right? So my sum, I can write s, is going to be a. What's a in this case? What's a? 5. Over 1 minus r. What's r? Yeah, it's 1 over 5. Okay, and even nicer, if I, instead of 1 over pi, I had pi in there, right, that would be greater than 1, so I'd say divergence. I didn't even find some. Okay, questions for me? I'm gonna do a couple examples real quick just to wrap up, but we'll be good after that, so I'm gonna. We have a couple other, that's kind of our big one. We have a couple of interesting series, well, one other interesting series you can work with for now, for the moment. But here's something else I need to give us as a tool for now. Okay, and so let me give you a couple comments here. We're gonna have comment 1 that if first comment rule, if I have a series and it's convergent, then I know that the limit as n approaches infinity of that term in the middle there is 0. Okay, why is this? Let's say that the limit was 1 instead. So the limit is 1 instead. What's going to happen is there's going to be some point far in the future of the sum where I just keep adding 1s. Is that going to convert? If I just keep adding 1s infinitely, is that going to be, no, it's not. I need to slow down something. I need to get to 0. Okay, that geometric series does that, but not all of them do. So this is convergent, then we know this is true. However, the opposite case is not always true. Right? Let me give you an example. Okay, this is called this 1 over n. This is called the harmonic. Harmonic series. Okay, it's got 1 over n. It's nice. Just your basic whatever power. Okay, what is the limit of that inside term as n goes to infinity? 0. Okay, this sum is divergent. The book is a proof, and I can actually show one, when we do the integral test here in a bit. I'll give you a brief approach for that. This is divergent. Okay, so even though it's the limit of the thing inside slows down to 0, the fact is that it doesn't slow down fast enough. It goes down to 0, but the terms are still a little big. So this is still divergent. So this is not collapsed to a value. This still blows up. So we need to be careful about this, okay? You cannot, if you see that the thing on the inside goes to 0, take the limit of it, that does not mean the series converges. However, what we do have from this is that if the limit as n approaches infinity of an is not equal to 0, then the series with an is divergent. Okay, so this makes a lot of series really easy, right? If you take that inside term and you see the limit of it goes to anything but 0, you can already say, oh, that I don't even have to bother. Okay, and we see that even with our example, right? Because if r is bigger than 1, right, the limit's not going to go to 0, it's going to go towards infinity, right? So it's going to be divergent. Okay, and this is the general rule, right? So the book gives a problem that's like the sum from n equals 1 to infinity of like k squared over k squared plus 2k minus 5 or something like that. If I take the limit of this thing, the inside as it goes towards infinity, is that going to be 0? What is the limit of the inside as it k goes towards infinity? What do you think? Yeah, it's k squared. K squared plus 2k plus 5. Just 1, right? That's not 0. So that means it's divergent. See that? Right? If it converges to 1, that just means I keep adding 1 infinitely at some point. And I don't want to do that. Okay? We want it to slow down. Okay, so this is good. So we can automatically rule out some things. Okay? You're gonna have to use that. You're gonna have to use some geometric series stuff as well to find convergence. Okay? I did some examples already. Here's another example. But that's general idea. Okay? So a couple of things to use. We're gonna get a lot more tools. Right, but those tools are dedicated for each section. Okay. Last thing. That's of importance. And I'll just do an example of this. Let's say that I have this series, right? And I want to know if this converges or diverges. Okay, so is this a geometric series? What do we think? Can I write this as a geometric series? The answer is no, right? Because the n on a geometric series is the power, right? Or it's definitely not a power here, right? This is a geometric series. That is not. Okay. What is the limit of the inside? What does it go to? Not infinity, right? It's 0. It's going to be 1 over infinity, which is 0. Okay. So we don't know for sure if it diverges. We still have to check. Okay. But looks a little awkward to work with. So what do we do in this case? Well, I don't like, I kind of have a hint here that I have n and I have n plus 1. Right? So is there some method we could use maybe to split those up? Split that up, rewrite it. Right, it's factored. And I split that up into 2 fractions. What is it? Well, it's true, it's multiplying, but that's not really 2 fractions. I mean, it's two fractions that are multiplying, but I want two fractions that are adding. Partial fractions, yes. We can actually split this up using partial fractions, which I don't have time, so I can't really get into the work on that, but some of them might be set up for you, depending. But this is 1 over n minus 1 over n plus 1. This is the same thing. Okay, and if you check it, you get n plus 1 minus n, so you get 1 on top. Okay, why is this significant? Let's take some numbers and plug it in. I'm going to get 1 over 1, minus 1 over 2. That's my first term, right? That's n equals 1. Plus 1 over 2, minus 1 over 3. Plus 1 over 3, minus 1 over 4. Plus 1 over 4, minus 1 over 5. Plus, and then let's just go to n right now. Okay, let's not go all the way to the end. Let's just do 1 over n minus 1 over n plus 1. What's gonna happen? Anybody see anything that's gonna happen here? Notice anything? So here we have a negative 1/2. Here we have a positive 1/2. They cancel. Here I have a negative 1/3, positive 1/3. Here I have negative 1/4, positive 1/4. Negative 1/5, positive 1/5. Negative 1/6, positive 1/6. Negative 1/7, all the way down. And then we're gonna have negative 1 over n times 1 over n, or plus 1 over n. So we're only left with first term, which is 1. And we're left with the last term, which is minus 1 over n plus 1. Okay. Now, is this my sum or is this a partial sum? Right? Did I go to infinity or did I just go to n? I just went to n, right? So I need to take the limit of this thing. What do you think? Is this convergent or divergent? Convergent, because that is a sum, and that sum in this case is number 1. Okay, cool. And this is called, by the way, this is called a telescoping. Yes,
So how do you know that you can use that test for divergence? I guess I'm a little.
We did. we did use it, right? We tried to. Right? Test for divergence says if the limit is not equal to 0, then it's divergent. That's the only thing we can say. If it does go to 0, we don't know. Okay? In this case, when we did it, the limit was 0. So it might still be divergent, but we don't know. We have to check. Okay? Does that make sense? So that test for divergence is an easy way to cancel one quickly. But if it's not 0, if it is 0, then you have to do a little bit more. Okay? Any other questions for me? Yes, it's called a telescoping series because it kind of like you're kind of looking far into the distance and see that everything kind of cancels, comes together. So it's truths. Okay, so you're stretching out the sum and seeing all the way down, and you just yeah, it just collapses, right? And then technically you could say if it just went on, you would know it would cancel, but it would just be like one. But it's safer to do this sort of limit for the thing, but just so you have it. Okay, is that good? Okay. I hate to not be able to give you more time, but I think I will have about 5 minutes for now, for break, if that's okay. I won't try to rush into it, like, the next section will be pretty easy. The book spends a long time on it. Too bad. This is by far probably the, well, that's, go ahead and take a break.